Hello and welcome back to Partial Differential Equations, the video series where we look at some specific PDEs and try to develop a theory for them. And in today's part 2, we start talking about a very important PDE called Laplace's equation. This one occurs a lot in applications, especially in physics when you have something like a potential. However, as always, before we go into the definition, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And as a reminder, you can use the link in the description to download additional material for the videos. For example, there you can find the PDF versions and quizzes for the videos. And then I would say, let's start with the topic of today by defining the so-called Laplacian. As already mentioned in the last video, this one is denoted by a capital delta and also often called Laplace operator. The term operator fits because it acts on functions and a new function comes out. And here we have a function u defined on Rn or on an open subset omega in Rn. And then the output space is just the real number line as always. And now the Laplace operator acted on u has a nice definition because it just uses the second order partial derivatives of u. More precisely, it uses the one with respect to just one variable, for example x1. And then the other ones are just added until we reach xn. So in short, we just have a sum with n terms, where n is the dimension of the input space of u. And in the case you want to write the partial derivatives with the multi-indices, you would say you have d alpha of u, where alpha is always of order 2 with an additional condition. Namely, only one entry alpha j is non-zero. So it has the same meaning as before, we use the second order partial derivatives, but not the mixed ones. And now by using this operator, we can define Laplace's equation as a PDE. And you might already know that it just says that the Laplacian of u should be equal to 0. So we search for the functions u that satisfy this equation on their domain omega. And here I can immediately tell you an application in physics. For example, you want to calculate the electric potential when there is no charge around. So at every point where there is no source, no charge, the electric potential should satisfy Laplace's equation. And in fact, at the end of this video, we can immediately write down some solutions of this PDE. However, first I should tell you that the solutions of this equation have a special name in mathematics. More precisely, we want to have solutions on an open set omega and where the partial derivatives of second order are still continuous functions. So in short, this means we search for a function u in C2. So you know this is the common notation for continuously differentiable functions up to order 2. So obviously for these functions we don't have a problem applying the Laplacian. And in the case we get out 0, we speak of a harmonic function. And you see, it's not hard at all to find examples for harmonic functions because all the constant functions satisfy Laplace's equation. These are not so interesting, so let's search for some more harmonic functions and maybe the ones with some symmetry. I say that because a radial symmetry allows us to completely solve Laplace's equation. So for the harmonic function u, we can take out the origin from the domain, so we consider it from C2 of Rn without 0. So in the case n is equal to 2, we can simply sketch the whole thing, which means we have the whole space except for one point. So seeing that in the application, you could say that we have a point charge at the origin and now we want to see what happens outside. And there it's quite natural to assume a radial symmetry, which means that the value of u only depends on the distance to the origin. Hence in our two-dimensional picture here, it means that for a given circle we find the same value for each point on it. And in the formula this would mean that u of x stays the same if you change the direction of x but not the length of x. Which also means that we already get all the values just by looking at one direction. So we can put these values into a real function phi that now only depends on the norm of x. And clearly what we mean here is the standard Euclidean norm in Rn. And obviously this function phi only has to be defined on the real interval from 0 to infinity. And the values are the same as for u, so we land in r. And moreover, a common thing would be to denote the radial variable by r. Hence, now everything is just about the function phi of r. So you see, if we already assume that u is harmonic, we need to apply the Laplace operator to this composition of two functions. And then we definitely know the conditions that phi has to satisfy in this case. So again, we assume that u is harmonic, so summing up these partial derivatives gives us 0. Therefore, let's first start with the first order partial derivative del u del xj. There we just have a chain rule because we have this composition of two functions. More precisely, we have phi of the square root of the squares added. So the Euclidean norm in Rn is not so complicated and we can definitely form the derivative. So the first thing we get here is phi prime of x in the norm, and then times the derivative of the square root times the inner derivative 2xj. So we have 1 over 2 times the square root, which we could write as the Euclidean norm again, times 2xj. So the good thing is we can already cancel the 2 and the whole thing is quite compact. Which helps us because we have to calculate a derivative again. Also not so hard because we just have to calculate with the product rule. So we immediately get here the second derivative of phi. And please don't forget, we also get out the inner derivative again. And multiplying that with the factor we already have gives us the same thing squared. And then finally the product rule tells us that we have a plus now. And there, if you want, you can actually do a quotient rule here for the remaining term. Which means we just have the denominator squared, so the norm of x squared. And in the numerator we multiply this with the derivative of the former numerator, which is just 1. And then we have minus xj times the same inner derivative as before. Hence you immediately see, here it's helpful to multiply with the norm of x in the numerator and the denominator. Because then we find the power 3 on the bottom, power 2 here and there. So actually it's quite nice, and now we can form the whole sum, and we already know it's equal to 0. And there you might already recognize the sum here for the first term gives us the norm of x squared in the numerator as well. So this nicely cancels exactly what we want to have. And then for the second part here, we also have the norm of x squared there. However, please note that we have a sum over n terms, which means that this constant term here actually occurs n times. And there we have it. This is what Laplace's equation tells us for the function phi. The second derivative plus the first derivative times n minus 1 divided by the norm of x is equal to 0. In other words, what we get out here is an ordinary differential equation for phi. So let's summarize that as our important result here. A radial symmetric harmonic function u on a pointed domain can be written with a function phi that satisfies this ODE. And we can write this ODE as the second derivative of phi at the point r plus the first derivative of r, which has the factor n minus 1 divided by r. And this should be equal to 0 for every r between 0 and infinity. So this is quite nice, and with our knowledge of ordinary differential equations, we can immediately solve this one. In fact, it's a linear one which we can solve with an integrating factor. So maybe it's easier to see if you write it as f of r as the first derivative of phi. Because then you just see that we actually just have a first order ODE to solve. And you might remember that the integrating factor just needs the antiderivative of the factor in front of f of r. Which is quite simple here because it's just the logarithm function. And since I don't want to confuse, I will use this common ln notation for the natural logarithm. And now the advantage here is that we can use the logarithm rules, which means we can pull in this factor as an exponent. And this is quite helpful because the integrating factor we need to solve the ODE is always given as e to the power of the antiderivative. So in this case, it's simply r to the power n minus 1. So this is the factor we multiply on both sides, and then we can just use this standard product rule. Hence, the whole differential equation can just be written with one derivative with respect to r. And we use that on the function r to the power n minus 1 times f of r. And now in this form the ODE is quite easy to solve, because we see that the function inside has to be equal to a constant on the interval from 0 to infinity. Which then implies that f of r is equal to this constant c1 divided by the function r to the power n minus 1. And obviously this inverse can also be written as r to the power 1 minus n. And with that we are almost done, because now we only have to integrate this function f of r to get our original function phi. And this already means that we also get in a second constant c2. Moreover, for this integration, we also have to distinguish two different cases here. You can see that in the formula of our function, because the case n is equal to 2 gives us the function 1 over r. And there we already know, integrating that gives us the natural logarithm function. Hence, in this special case, we have c2 plus c1 times ln of r. And this is the only special case, because for a larger n we just have a general formula for the antiderivative. Namely, as you know, we just have to increase the exponent exactly by 1. So we have r to the power 2 minus n with the same factor in front. But honestly, we could push this factor into the constant c1. And there we have it. These are all possible radial symmetric solutions of Laplace's equation on the domain Rn without 0. And often in applications, as already mentioned, the three-dimensional case is important, and you see we just have the function 1 over r here. And soon we will see that this is actually what we call a fundamental solution of our PDE. Therefore I would say, let's continue with that in the next video. So really hope I meet you there again, and have a nice day. Bye bye.